So what I'm going to talk about now is how we think about the mass of individual atoms. And so what we could do is weigh individual atoms and report their masses in grams or kilograms. But as you might expect, and as you saw in the earlier slides, it is an extremely small number. So what we do is when we talk about the mass of individual atoms, we switch to a new unit system. Instead of looking at the mass of atoms in terms of grams or kilograms, we look at the mass of atoms in a unit system which is called atomic mass units, or AMUs for short. They can also be called U's if you want. So the first thing I want to do is sort of define what one atomic mass unit is. And so I think the best thing for me to do is sort of to draw that out. So let's say we have a carbon-12 atom. And so what I'm kind of hoping you know already is you can look at that hyphen notation and you know the number of protons, the number of neutrons, and the mass number. So with carbon, you can look up on the periodic table that its atomic number is 6, and so it has 6 protons. Because the mass number is 12, hopefully you will know that it has 6 neutrons as well. But let's first talk about, again, how we define an atomic mass unit. So let's say we have one atom of carbon-12. So here it is. And so what I'm going to do is divide this atom into 12 equal parts like this. And this is not the best, but it'll have to do like that. So we should have 12 equal parts. So let me just kind of number these parts really quick. Okay, so it looks like we do have 12 equal parts. Well, take out 1/12 of this carbon-12 atom, one of these parts, 1/12 of this. This is 1 AMU. So this is also an exact number. So what I want you to know is that 1 AMU, which is an exact number, is 1/12 of a carbon-12 atom. That is the way it's defined. Now let's go a little bit further than this. Okay, so we have carbon-12, and we have protons, and we have neutrons, and we have mass. So as we kind of figured out, carbon-12 has 6 protons, 6 neutrons. And now again, we're reflecting mass, not so much in grams or kilograms, but in atomic mass units. Now, if 1/12 of the carbon-12 atom has 1 atomic mass unit, and that's an exact number, can you tell me how many atomic mass units a whole carbon-12 atom has? Well, you just take that 1/12 of the carbon atom, which weighs 1 AMU, and multiply by 12 to get the whole carbon atom. And so one single carbon-12 atom should have exactly 12.000 atomic mass units. Again, this is sort of an exact number. So remember that when you're dealing with the carbon-12 atom, it is useful to know that that has exactly 12.0000 atomic mass units. Now let's talk a little bit about another isotope of carbon, which is carbon-13. So I'll draw a carbon-13 here, and so it has 6 protons because it's a carbon atom, but it has 1 more neutron, so it has 7 neutrons. So what you may have seen is that since 1 AMU is 1/12 of the carbon-12 atom, that 1 AMU is going to be approximately the weight of one of those protons or neutrons, right? So if you have 6 protons and 6 neutrons, and just assuming for the moment that each one weighs about 1 AMU, we have a total of these particles, we have a total of 12 of these particles, and so it should weigh 12 AMU. So with carbon-13, since we have a total of 13 of these particles, it should weigh a little bit more. It should weigh 13 AMU. And it's not exactly that for reasons which we'll learn about in the second semester. It's a little bit more than that. It's 13.0035 AMU. Now here's a question for you to consider. In light of the fact in nature, the percent abundance of carbon-12 of all carbon atoms in nature is about 98.9%. Of carbon-13 atoms in nature is about 1.1%. Now there is an isotope called carbon-14, and there are other isotopes, but they're at such a tiny percentage in nature, like 0.00001%, we really don't have to worry about this in this sort of question I'm posing for you. So, if that is the case, can you tell me what the average atomic mass is of carbon in light of the fact that 98% of those atoms are carbon-12 with a certain weight, and 1% of those atoms are carbon-13 with a different weight? How would you figure that out? So what we're trying to do is figure out the average atomic mass of carbon. So one question to ask yourself is this: would the average atomic mass of carbon be exactly the same as the atomic mass of carbon-12? And the answer is no, because we have a little bit of the heavier carbon-13 mixed in. So we would not expect the average atomic mass of carbon to be exactly 12.000. It's going to be a little bit more than that. But the question is, how do we figure out how much more it is? Well, there what you do is you calculate something called a weighted average. And I'm going to do that in a second. But before I do that, let me just give you a simple example of a weighted average. So I'm going to erase this for the moment and go on to a problem. Okay. So problem 1 is sort of a typical example of a weighted average problem. So let me read it out. It says, let's say that you have a 90 on your test. Now let's say your tests account for 8% of your total grade of the class. Now let's say you have 70 for your homework grade. And let's say that that accounts for 20% of your final grade in the class. What is going to be your average grade for the class? Well, what you want to do is you have to calculate a weighted average of the test grade and the homework grade. So let me show you how you would do this. So here on the screen here we have homework and we have test. Now what we saw is that the homework grade, it looks like it's going to be 70. And the test grade is 90. Now, if we average those two together and divide by 2, that would not be the correct answer. And the reason is that the final grade is not calculated from being 50% homework and 50% test. It's something different. It's 20% homework and 80% test. So what do? What you have to do is take those numbers and weight them by the percentage that is going to be accounted for in the final grade. So with homework, it's going to be 20% of the grade. And so what you want to do is take the homework grade of 70, and you don't want to multiply it with the percentage. You want to multiply it by the decimal form of that. So the decimal form of the percentage is going to be 0.2000. Okay, so for the test, the score is 90. And so again, you want to multiply that by the decimal form of the percentage. 80% is going to be 8,000. And then what you want to do is you want to add these up, whatever these numbers are, and that should give you the average for the class. So let's go ahead and do that. So I'm going to get my calculator here. Okay, so 70 times 0.2 is 14.0000, and then 90 times 0.8 is 72.0000. Okay, so if you add up these numbers without even considering significant figures right now, what would the answer be? The answer would be 86.0000. Okay, so let's just do significant figures and make sure that this is rounded to the correct number of significant figures, because you'll have to do this with a weighted average problem you're going to get with the isotopes. So what you can first see is that the first one we did was a multiplication. And so we would have to sort of consider how many significant figures that number has as the result of the multiplication. So there are 2 significant figures here. There are 4 significant figures here. And so we should think about rounding this answer to 2 significant figures, because the answer shouldn't have as many significant figures as the number with the least number of significant figures. Same thing with the second one. We would think about rounding this to 2 significant figures, and I'm highlighting the uncertain digit. So in the last step, you're adding 14 and 72. So that is an addition. So for the last step, you apply the rules for significant figures for addition. And so there, you're going to round the answer so its last uncertain digit is going to be in the same location as the one that's furthest to the left. And those numbers up here, there's not one that's furthest to the left. Both of them are in the ones place. So we want to round this to the ones place. So the weighted average for this example would be 86, which kind of makes sense if you think about it. So we have most of the grade, 80% of the grade is going to be toward tests, and you got a higher score for that. A small percentage of the grade is going to be toward homework, which is 70, which is a lower grade. You would expect the average, because it's so heavily weighted by the tests, the average to be closer, much closer to 90 than to 70, and it is. It has a value of 86. And so weighted averages are a great way to calculate averages for a class when you consider the relative percentages that you have. Okay, so let's go to another problem. Let's go to carbon 12 and carbon 13. So in problem 2, let's say that carbon 12 has a mass of 12.000 AMU and it has a 98.9% abundance in nature, and that carbon 13 has 13.0035 AMU and it has a 1.1% abundant in nature. I'm also noting here that we're just not going to consider carbon 14 and other carbon isotopes because there's just not a lot of them in nature. So the question is, given that information, can you calculate out an average atomic mass for carbon? So let's go ahead and do this problem here. So we have carbon 12 and carbon 13. And so let's write down what the atomic mass for carbon 12 is. It is 12.0000, and I'm just going to leave out AMU. How about for carbon 13 is 13.0035. Now the first thing we're going to do is for each of these numbers, we're going to multiply them by their abundances. And so we're going to convert the abundance of these isotopes into their decimal forms. And so carbon 12, there is 98.9%. So we're going to multiply by 0.9890. Carbon 13, its abundance is 1.1%. So the decimal form of that is 0.0110. And so we'll go ahead and do that and see what numbers we get. So it's going to be 12 times 0.9890. And I get 11.8680 for carbon 12 is the first number. And then for carbon 13, it's 13.0035 times 0.0110. And I get 0.1430. These numbers are going to be added. So what do I get? Plus 11.8680. I get 12.011038.5 on my calculator. So here, what I've just done is considering the relative abundances of these two carbon isotopes, 12 and 13, I calculate what the average atomic mass of carbon should be. Now the last thing you need to do is round this to the correct number of significant figures. So let me do that pretty quickly. So we have 6 significant figures here, we have 4 significant figures here, and so this number, if you were to round it, you're not going to, would have 4 significant figures with this number in the hundredths place being the uncertain digit. Again, 6 significant figures here, 4 here. So here we have these 4 numbers would be significant with the 0 here in the 10,000ths place as the uncertain digit. And so here the final step is an addition. And remember, the uncertain digit is going to be located in the same place as the uncertain digit in these numbers that is furthest to the left. The one that's furthest to the left is in the first number. It is in the hundredths place. So we round this to the hundredths place. So the average atomic mass of carbon in nature is 12.01 atomic mass units. And again, I'm hoping at this point you know why it's not 12.00. And the reason is, although most of natural carbon is of the carbon-12 isotope, which has a mass of 12.000 AMU, there's a little bit of carbon-13 mixed in there. And so that bumps up the average mass for natural carbon a little bit. And so actually those numbers, the average atomic masses of elements, when you consider the proportions of the isotopes of those elements, they're also called atomic weights, and they're always found in the periodic table. So if you look at this periodic table I'm going to show you here, so what you can see here for each of these boxes, for example, have carbon here. In this particular periodic table, the atomic number for the element is at the top left. The atomic number for carbon is 6. However, the number below the symbol there, that is the average atomic mass for carbon or the atomic weight. And so whenever you look at a periodic table and you're looking at an elemental box there, if you see an integer, that is probably the atomic number. If you see a larger number that is in decimal form, remember that is the average atomic mass for that element, also called the atomic weight of that element. So I'm going to do a couple more problems. Okay, problem number 3 is a good thought question. Okay, problem number 3. There are 2 isotopes of boron in nature. They are boron 10 and boron 11. The atomic weight, or the average atomic mass of boron, considering the abundances of the boron isotopes, is going to be 10.81. Now, can you tell me, is there more boron 10 or boron 11 in nature? Okay, this is sort of a qualitative question, but let me see or show you how I would work this out. So again, there are 2 boron isotopes. There's boron 10 and boron 11. And so we have a little bit of information about them. We know that the atomic weight, or the average atomic mass of the boron isotopes all mixed together, is going to be 10.81 AMU. So the question is this: from this basic information, can you figure out which of these isotopes of boron is more predominant? Is it 10 or 11? And actually, you can make some reasonable guesses and figure out which isotope is more predominant. So one thing you can do is maybe you can look at this hyphen notation of these boron isotopes, and maybe you can figure out approximately how many protons and neutrons are going to be in each of these isotopes. Okay, you could look up on a periodic table what the atomic number of boron is. That's something you could easily do. And if you looked it up, the atomic number of boron is 5, so it should have 5 protons. So if the mass number is 10, it should have 5 neutrons. Now with boron 11, it will also have 5 protons because it's boron, but it has a mass number 11, so it should have 6 neutrons. Now, based on this information, can you give me some sort of approximate value of the relative masses of these isotopes? And so remembering that 1 AMU is about the mass of 1 proton or 1 neutron in an atom, you can sort of make a guess as to what the mass of each of these protons is, what the mass of each of these isotopes is going to be. So if boron 10, it has 5 protons and 5 neutrons, so we might expect the mass in AMUs to be around 10. It's not going to be exactly that, but it's going to be around that. With boron 11, there are 5 protons and 6 neutrons, and so we might expect the mass to be about 11 AMUs. Okay, now think about this question. If you have 50% boron 10 and 50% boron 11 in nature, what would you expect the average mass of boron to be in nature? Well, it would be the average of 10 and 11, it would be 10.5, right? But that is not the case. It looks like that's going to be a larger number, larger than 10.5, closer to 11, which suggests that there's probably more boron 11 in nature than boron 10. So that would be the answer. Boron 11 is the more predominant isotope. Okay, so let's go on to the next problem. Okay, problem 4. 3 isotopes of silicon occur in nature. So we have a listing of the silicon isotopes and their abundances and percentages, and then we have their atomic masses. And you're asked to calculate an average atomic mass or atomic weight for silicon. So let me show you the basic setup for this, but I won't go through the math, but I'm kind of hoping that you'll understand how to set up the problem. Okay, so this is what you do. So you have silicon 28, silicon 29, silicon 30. And so what you want to do is write out their atomic masses, and so it's 27.97693 for silicon 28. For silicon 29, it's 28.97649. For silicon 30, it's 29.97377. And then for each of these atomic masses, you remember that you take the percentage and convert it to a decimal, and you multiply that by the decimal abundance. So for silicon 28 is 0.9223. This number would be multiplied by 0.04680, and this number would be multiplied by 0.03090. So what you would do is multiply the atomic mass unit mass for each of these isotopes by its decimal value of its abundance and get a number. And then you add up those numbers, and that should give you the average atomic mass for silicon. And so it's going to be a very large number. And then what you'll have to do is correctly round it off to the correct number of significant figures. So the answer should end up to be the average atomic mass or atomic weight of silicon, considering the relative abundances of these different silicon isotopes, should be 28.09 atomic mass units.